All right, so this part of Unit 2 is going to focus more on the mathematical side of reactions. We're going to start with lab stoichiometry. You have two reactants here, magnesium and hydrochloric acid, and you have different amounts of magnesium and hydrochloric acid. If you compare the first two, you've increased the amount of hydrochloric acid, and we see the balloon size has increased as well. Whereas with the last two, we see that we have increased the hydrochloric acid, but the balloon size has not changed. And so what we're going to see as we go throughout this is that the reactant amounts are basically in a ratio between the one another, and that's going to depend on how much of those products you can actually form. So we've talked a little bit about a couple of these terms already, but I do want to make sure that we just touch base and that you're comfortable with all of them, because you're going to see these a lot in the problems we're going to be doing. Limiting reactant and excess reactant obviously are both dealing with reactants, but your limiting reactant is the one that determines how much of your product can actually get made. It's the reactant you're going to run out of before the other reactants that are present in your reaction. Your excess reactant, there could be one or more, is the reactant that remains, that's left behind, that you didn't completely use. And there are times when you can have both reactants be limiting. If you have two reactants and you use them both completely, then you would actually not have an excess reactant. But more often than not, the more inexpensive reactant serves as your excess reactant, just to make sure that you completely use up that limiting reactant as fully as possible. The actual yield is what you have prepared in an experiment. In a problem, I would have to tell you that it's the amount that was actually made. But it is extremely rare for a chemical reaction to go perfectly, like pretty much impossible. And so the actual yield is just representing the amount that was truly formed. The theoretical yield is if everything went perfectly, based on your limiting reactant, how much of the desired product you could actually form. Percent yield allows us to look at the amount that was actually made and compare it to the amount that should have been made in theory. And so we get an approximate idea as to what percent of our product we actually were able to make. So the first example we're going to do involves mercury and bromine. We see that when those two elements combine together, they make mercury bromide. I want to know how much mercury to bromide can be made when I combine 10 grams of mercury and 9 grams of bromine. So if you have one of these problems where you have amounts of both reactants and you want to figure out how much of the product you can make, one way to do this is to take each reactant's starting amount and figure out how much of that product you can make from it. So we're going to do two stoichiometry problems, starting with the mass of mercury, and we're going to convert it to mercury to bromide, figuring out how much of the mercury to bromide can be made from 10 grams of Hg. So I went from grams of mercury in my denominator, and I put grams of mercury to bromide in my numerator. Grams gets molar mass, so that's where that 200.59 came from, Hg's molar mass on the periodic table. And then HgBr2 would be the 200.59 plus 2 times 79.9 for the two Brs. And that gave me a mass of 360.39. I need to look at my balanced equation to see what the stoichiometric ratio is between Hg and HgBr2. And I see that those are in a 1-to-1 ratio. The grams of mercury cancel out, and at this point I can multiply and divide and determine how much, in theory, if I consumed all of the mercury and it had plenty of bromine, I would be able to make of mercury to bromide. And I got that that would give me 18.0 grams. I wanted 3 sig figs because my molar masses each had 5 and my starting value had 3. I'm going to repeat this process with bromine, taking my 9 grams of bromine, and this time I'm going to get rid of grams of bromine, and I'm still going to be finding grams of mercury to bromide. If you happen to have more than one product, you can pick whichever product you want to use, but you have to compare, in terms of limiting and excess reactants, the same products to each other. So I would take the molar mass of bromine, 79.9 times 2, and then the molar mass of HgBr2, 360.39. I look at my balanced equation to see the stoichiometric relationship between bromine and mercury 2 bromide, 1 to 1, and I multiply and divide. I want 3 sig figs in my answer, and this time I got that I could make 20.3 grams of HgBr2 from 9 grams of bromine in an unlimited supply of mercury. Remember we said the limiting reactant is going to be the one that determines your theoretical yield, and so the one that produced the smaller amount of product is the one that you're going to run out of first. So since mercury made the smaller amount of product, it is acting as my limiting reactant. Bromine producing almost 2 or a little more than 2 grams more would be my excess reactant. And so the mass of mercury 2 bromide would be 18 grams. That's the amount that I can make before I run out of bromine, before I run out of mercury. At that point, I would not be able to make any more HgBr2. So here's an example for you all to try. You do need to make sure you balance the equation. We have 45 grams of lithium. It's reacted with 300 grams of AlCl3, and it made 55 grams of aluminum. So that 55 grams is what was made in the experiment. So that's your actual yield. And we want to know what was our theoretical yield. Again, in this equation, you have two products. Since you know the actual yield for aluminum, I would find the theoretical yield for aluminum using my masses of my two reactants, just like I did in the previous problem. But if I have to balance my equation, I look at my lithiums, I see they're balanced. I look at my aluminums, I see they're balanced. But I see that my chlorines are not. And since chlorine's not balanced, that changes lithium. And I believe now you do have a completely balanced equation. With my balanced equation, I can take my 45 grams of lithium and determine how many grams of aluminum could be made. Again, I chose aluminum since I was told about the actual yield of aluminum in this experiment. Grams of lithium go on the bottom, grams of aluminum go in the numerator, molar masses for both go in the numerator and the denominator, and now I need coefficients to relate the two substances, 3 lithiums for 1 Al. I multiply and divide. I want 3 sig figs in my answer, and I got 58.3 grams of aluminum could be made from 45 grams of lithium if I had more than enough AlCl3. I was told I had 300 grams of AlCl3, so if you just look at it by mass, it looks like lithium's got to be the one that determines my theoretical yield, no brainer. But we have to go through and do the math because remember, grams don't compare necessarily to individual elements. Moles are what we can compare between different elements or between elements and compounds. So I want to get rid of my grams of AlCl3. I want to find my grams of Al. Aluminum chloride would be 3 times 35.45 plus the 26.98 for the aluminum, 133.33. Aluminum's mass is going to come from the periodic table, 26.98. And if I look at my balanced equation, I see that AlCl3 and Al are in a 1-to-1 ratio. So at this point, I can multiply and divide. I have 4 sig figs in the aluminum chloride, 4 in the aluminum molar mass, and 5 in the AlCl3 molar mass. So I want 4 in my balanced equation, 4 sig figs in my mass for aluminum. And so it was bigger, but probably not as big of a difference as you might have thought just based on their initial masses. Because of that stoichiometric ratio between lithium and the fact that you had a much smaller amount of lithium, it was a little bit closer than you might have anticipated. So my theoretical yield is determined by my limiting reactant, the one that can make the smaller amount of product, which would be Li in this case. So 58.3 grams of aluminum is the maximum amount of aluminum I can make from mixing these two reactants with one another. If I want to calculate the percent yield, I need to have an actual yield and I need to have a theoretical yield. Again, they both have to be of the same substance, which is why we found the theoretical yield for aluminum, because we had the actual yield for aluminum given to us in the problem. If you were doing in the lab, you would get your actual yield from your data. So I can take the 55 grams of aluminum and divide it by the theoretical yield of 58.3 grams and multiply it by 100. And when I do that, I get my percent yield, which in this experiment happened to be 94.3%. All right, and I have one last part for this to do, and that is to figure out how much of my excess reactant actually remains. I know I used up a lot of my excess reactant, but I don't know how much is going to be left behind. I do know that I used up all of my limiting reactant, and if I used up all of my limiting reactant, I should be able to figure out, in theory, how much of the AlCl3 would have been consumed by 45 grams of lithium. If I want to know how much actually remained overall, I need to know how much was used, and I need to know how much I started with. And the difference between those would help me determine the mass that remains. Well, I know how much I started with. I had 300 grams to begin with. But I'm going to use that relationship I talked about between lithium and aluminum chloride, and there's multiple ways you can do this. But we're going to use that relationship between the two reactants to determine how much AlCl3 was actually consumed. So I'm going to take my 45 grams of lithium and do one last stoichiometry problem, going from grams of lithium to grams of aluminum chloride. Molar mass for lithium gets placed. Molar mass for aluminum chloride, you did that one previously as well, 133.33. And now I need to look at the stoichiometric relationship between the two reactants, 3-to-1 ratio. The grams of lithium cancel out. I multiply and divide. I should have 3 sig figs in my answer. And I get that 288 grams of AlCl3 were needed to completely use up the 45 grams of lithium. So that's how much was actually used. I know how much I started with, the 300 grams, so if I take the difference between 300 and 288, I should be able to determine how many grams of AlCl3 remain, and that would be 12.